All right, greetings, gentlemen. Okay, so there's been a massive CAD update today, which is February 21st, 2019. Okay, so in the past 2 days, Andrew has spent about, by my figures, 15 hours anyhow, at least. I'm just going by the timestamp, so when he committed things. Um, just going through, we finally last night finalized the last few things on the Eccentric drive. Um, I've tried to make this as much of a retrofit as possible. So some holes that you have in your cradle base sides you won't use. You'll have to add some holes in your cradle base sides. Things of that nature, okay? G plates. If you already have a hole in there, you're going to have to add an additional hole. I'll try to remember to cover all these things. But so this particular assembly you'll find in, I believe, let me look here real quick. Yeah, you'll find it in the current CAD. So it'd be J5 project, current CAD, complete assembly, common, lower half assembly. Okay, so that's where you'll find this. Okay, so close that. Okay, eccentric drive. Okay, hopefully this animates correctly. It's a very complex assembly, and well, at any given time, SolidWorks can completely screw the pooch. So this was the general basic concept I had with it. It goes full up, okay, and it goes full down. It toggles at each endpoint inherently, okay? So there is very little torque that's retransferred through the drivetrain for the eccentric drive, okay? So it's inherently robust. The other thing is, being that it's an eccentric drive, if when a malfunction occurs, okay, not if, when, okay, you forget to plug in a pot wire when you assemble the thing. A pot wire comes loose, the speed controller malfunctions, a software issue commands the speed controller to just keep going, whatever. The system will not destroy the robot. As with linear actuators, if there's an issue, bad things happen pretty much instantaneously. You're going to break a bunch of stuff, and there's so much forces involved there that you literally could potentially just rip the cradle base in half. There's that much force. So trust me, that yeah, bad things can and will happen with linear actuators. So, okay, so that's the way this works. Okay, this is the the eccentric motion here. Now a change. The original plan was that this could go in forward, or backwards orientation wouldn't matter. What I realized is that I realistically could not do that with a feedback system, because it's an eccentric drive. It's a reciprocal system, so it's not a pure linear relationship. It would have varying amounts of speed throughout the travel. When it got to the endpoints, it would be very difficult to get them, to start and stop exactly where it needed to be. It needed to be a pure linear function for the feedback system. So when we operate this, the way it's designed to operate now is it will operate in this orientation here, which is 180 degrees only. So it will have a full down position, and then it will come back, and it will only operate in this particular arc of motion, okay? But when a malfunction occurs, okay, there's nothing in here that will be damaged or destroyed if it just keeps rotating, an infinite track tip, going crazy thing, okay? So how is that achieved? Okay, so I'm going to open up the eccentric drive proper. Don't get scared. This is the eccentric drive, okay? Yeah, let it soak in. This is using the same exact gear motor configuration that we're using for one side of, one track. Okay, we have that going into a 10-tooth Tsubaki 10-tooth sprocket. That goes into a Tsubaki 54-tooth sprocket. That then goes into a Azura, I don't know, 8-tooth. This is a jack shaft sprocket. It has a key integrated into the gear itself. That is to say that, yeah, the keyway is part of the actual gear. It's the only way I could, yeah, these are used on mini bikes and things like that. Should be very robust. That is a number 42 sprocket, or a number 40 chain, or number 40 sprocket, number 40 chain. So we jump from 35 to 40 because this is on the man side of things, okay? And then from that 8-tooth sprocket, we go into a 44-tooth Tsubaki sprocket here. And that keys into our eccentric drive, which is our eccentric lobe, which is right here, okay? And if my math has been correct and worked out, yeah, it should be able to do full up, from full down to full up in 4 seconds or less, okay? Load dependent. A lot of this it's theoretical. There's been no inefficiencies calculated in. Well, I have just off the, hey, okay, it's going to go a little bit faster, but because of the weight. But trust me, yeah, I'll know when I build the damn thing. Which is coming next, the prototype, okay? The prototyping of it. Okay, so how is this doing the feedback system? Well, it's doing the feedback system. I'm going to hide this outer plate through here, okay? That's fully defined and can't move, but fortunately, I have one right here. 3D printed sprocket. A 3-turn potentiometer, 3-turn 5K potentiometer that goes into our motor controller. It has hex standoffs in here, which are 1¼ inches long. Okay, so basically this thing sandwiches between the 2 aluminum plates. The sprocket, whoops, yes, you got to be able to see it, not me. The sprocket, and this is upside down, but the sprocket keys in like this. As the sprocket turns, oops, it turns the feedback pot. For every 180 degrees of rotation of this, that translates to 1.375 rotations of this pot. Now, there's a safety feature built in. What if, well, when things go awry and there's a malfunction and the thing keeps tipping, our potentiometer is only good for 3 turns, okay? So anything over 3 turns, and it will do that. It will hit the end stop. But guess what? This is just a slight friction fit. So the gear can continue spinning. The potentiometer stops. No damage to the pot. No damage to anything, okay? And then it's just a matter of figuring out what you screwed up, putting the tracks back down into position, and then retuning this potentiometer. How do you do that? Okay, well, you simply go in here, because there's a hole in the side of the cradle base. You can access this pot like this, and you simply turn it until you get it retimed. Okay, so there you go. Yeah, and the wires for the pot exit out the bottom, which is in the CAD. It is down here, right there. There is no chain tensioning provision for the number 40 chain. It is quite stout, quite robust. If it gets a little bit of slack in it over time, don't know what to tell you. Hey man, there's no room to, I've squeezed this much crap into, 10 gallons of crap into a 5-gallon bucket. I can fit no more in here realistically. Okay. Our eccentric is attached via two 3/8 inch sized button head cap screws, and you can see that here's a precision clevis pin 3/8. That is our rotational point. Remember, yeah, there's going to be grease in here. It's going to be lubricated. This isn't a high speed mechanism. It's very slow. Yeah, we won't have a problem. A little bit of grease on the chains, whatever. Now I do have a provision up here for this number 35 chain, obviously. A tensioning system which is built in, which is done by the fact that hide that yeah, there's slots in this plate to be able to move that motor forward or backward to tighten or loosen the chain. Okay, power is transferred through this unacceptably expensive coupling, but hey, it's a necessary evil. Power is transferred through here to the slave side, which simply, you know, hey, turn it here, things happen here. Okay, yeah, so there it is. Kind of got an idea. I went with, you know, standard size bearings here, you know, 10 R10 to RS bearings instead of the old design had two of these large bearings in there, and then machining of, you know, this hub actually went into the bearing, and I realized, God, that is, yeah, it was a bad way of doing it. Just flip the sprocket around, left the hub as it is. Collar in here again, this way if set screws come loose or whatever, things are still going to stay in their relative position. They're only going to move 5 or 10 thousandths of an inch one way or another. It's not going to be a catastrophic situation. Spacers in here again, in case the set screws come loose, things work loose over time. You'll never know that anything's wrong unless you go in there and say, hey, my set screws are loose, or hey, the set screws are gone. You know, the system will continue to function. It's very robust. It should be bulletproof. There are the back of the plate is held coincident to the cradle base side plate by this through bolt here, and then there is some torsional bolt screws that I put through here that will absorb, because there's a lot of pressure, guys. We're talking hundreds and hundreds of pounds. This thing may want to try to go up or down on us. That's what these 3 button head screws, you know, stop. The whole thing's rock solid. It's in there. Yeah. So we go back to the full assembly here. Again, try to give you some context. So yeah, let me see here. See what I can hide. Okay, I can hide this. Yep. Please excuse my poor skills here. This plate here is currently steel. Might be okay with aluminum. I just don't know. Steel, hey, it's cheap enough. So you're going to be able to see this more in the CAD. We have shaft couplers here to prevent these upper A-frame linkage rods, which are now half-inch thick pieces. So this is what I nicknamed them the hockey stick. That's what it is. That's what it has to be. The system literally, I mean, this stuff barely works. It barely fits. It is what it is. I can do pretty much nothing more. This will have to be done CNC. Again, it is what it is. I mean, yeah, we're way outside of the envelope here when it comes to, yeah, I can't change the damn robot to tweak something or fit something in. I have to work within the original design of the original robot. So, okay, so those are steel. These arms here, yeah, these are steel. These are 750 thousandths thick. Okay, They can't be aluminum because I can't go any bigger on this outer, it's got to be steel, because if it's aluminum, it's too thin there. I think it's 300 thousandths, I think, is the wall thickness. Yeah, zero point 0.3. If I did that in aluminum, yeah, we're talking huge amount of force. Think of this like a connecting rod in an engine. Yeah, it's got to be big, beefy, large, and in charge. If it isn't, boom, it's going to fly apart. So it's got to be steel. So is what it is. It's, God, I wish it could be something different, but yeah, this is, quite honestly. The chamfer here, yep, kind of got to have that in there. Chamfers add strength, or fillets, I should say, fillets. And we need to keep it a certain size because it needs to clear the damn number 40 chain. There's just a variety of different, I mean, dear God, when you look at this, you look at the hockey stick, look how close this outside diameter comes to this hockey stick as it traverses through its travel. It's insane. Like there, I mean, yeah, not a lot of room. And the same thing goes if I hide this. You can see that the actual hockey stick, the distance between the hockey stick top and the top of our cradle base is not that great. I mean, we're talking, maybe a quarter of an inch there, not a whole lot. So care is going to need to be taken, that, don't try to, cowboy this. Get it right. If the geometry is not right, it's not going to work right, okay? Now, there's some of you going, well, what if this eccentric is ever so slightly not, for whatever reason? There is an adjustment, and it's actually pretty simple. So say you do the track tip here, okay, and you're all the way down. There we go. You're all the way down. But let's say that this track, it's slightly off. It's a little bit back, or maybe it's a little bit back. Okay, that is adjusted out by the pressure in your rear tire. That dictates how this thing sets. Okay, so you're basically raising or lowering the ass end of this thing. That will give you, and it's not a magic bullet. Okay, we're only talking machining, parts fit, a little bit of, oh, this wiggles a little bit here, that wiggles a little bit there, all those cumulative kind of things. That's the only thing that adjustment, that pneumatic tire adjustment, the pressure is meant to account for, not for, oops, I put a hole a quarter inch out of place, in the wrong spot. Oh, it'll be fine. No, you're screwed. Okay, go back, remake it. Yeah. This geometry is critical. If it's not right, if it's not within, few thousandths of an inch, you're going to start having issues, and you're going to see it. Okay, so again, attention to detail. It's got to be right. The other thing I want to add in here too, for God's sake, this has only been me and Andrew looking at this. Okay, I need all eyes on this. Okay, pick it apart. If you see something that you don't think's right, or something that's just blatantly wrong, for God's sake, point it out now. Okay, don't be afraid to open your mouth. Let me know. Hey, this is wrong. Someone screwed up. We'll look into it, see if someone did screw up. We're human. Okay. Andrew does things, we come up with a design. I say, okay, we need to change this, and this. And Andrew goes and makes those changes. And maybe he didn't understand exactly what I was telling him I wanted, or maybe he got a number wrong. Yeah. Okay. There could be errors in here. So for God's sake, people, take the damn time to look at this and study it and understand how it works and how all the parts interact with each other and how all the geometry works, and do your measurements and stuff. And if something's not right, speak up now. or forever hold your peace. Thankfully, it's a robot, so it's not like you got one shot at it and then you're, I mean, but it's going to cost more money if you have to go back. What's the old saying? There's never time to do it right, but there's always time to do it over. Yeah, exactly. So if we don't, yeah, it's got to be done right the first time, or you're going to be doing it over. Okay. So, um, yeah, I'm sorry, I don't mean to waste, I'm trying not to waste everybody's time here. I cannot tell you that, well, I could tell you, but I'm not going to tell you. A tremendous amount of time and money has gone into this. The R&D, it's going to cost more than I expected, but in the overall scheme of things, it will be far less than if we tried to go and get actuators that were custom actuators that only traveled, this distance in this distance, and they physically were incapable of going any further because actuators just get ridiculously expensive. And the actuators that are needed for this to do it in the amount of time we need to do it really aren't made. I mean, to use an actuator-based design, you need to move 1 inch per second, okay? Because it's about a 4-inch stroke, okay? And you need to do that in 4 seconds to be screen accurate, okay? And you say, oh, okay, yeah, not a problem. 4 inches, 4 seconds, no problem. Okay, yeah, but yeah, guess what? You need to do that with about, 1,000 pounds of force, at a minimum. Oh, well, there's your problem. You can get very powerful actuators, but the trade-off is that they're geared way down. They are slow. So yeah, yep. And I'm sure some company out there would make you an actuator or something, but man, the cost alone would be ridiculous. And again, you have to have that exact travel. Anything too far forward, anything too far back, and things just start bending and snapping and ripping apart and breaking. The eccentric drive solves all that. So with all of that being said, I have not actually built the eccentric drive nor tested it. Yeah. This is all on me, guys. This is all my head, engineering in my head, and I'm not an engineer. This is, I'm 99.9% sure that this will work. But hey, man, I've got to see it work first. So, the eccentric lobe, steel. Arm, steel. This hockey stick thing here, steel. The cam, I think we changed back to aluminum. Might be, I mean, it's fine for the bottom, but the problem the one problem I do possibly see, and there again, it depends upon how much weight is at the back, and really the A-frame really doesn't have that much weight to it. Okay, the center of gravity of this thing is actually like somewhere in here. But anyhow, my biggest concern is to squeeze all this in here. We had to offset this arm from this cam. Before it was a inline center, and we can't do that now because it would hit the damn chain. So I had to offset that. I don't know how much torsional force that will generate. I don't think it'll be a problem, but it is a concern I have. So I am keeping that in mind. And I have kept that in mind. Like I mentioned, G-plates, yeah, there's now a hole down here. There's a cutout on some of yours. I think this hole just goes in here. It'll just be an add-in, okay? That is so you can get through, so you can insert the pin, the clevis pin in through here when you're assembling it or disassembling it or doing maintenance. No, you don't need to do no stinking maintenance. This thing will last forever. It's the way I designed it. Yeah, and that's the thing. I designed it so that, yeah, unless you're like just doing stupid redneck crap with this thing, just above and beyond any degree of reason whatsoever. This thing is built like a tank, literally. Okay, yeah. Um, I don't think there's a weak point. Well, yeah, technically, but there again, it's steel. I think the weakest link is just this wall thickness here. But there again, that's why I'm making it steel. Um, so there you go, guys. For God's sake, open the CAD. Look at the design. Don't just watch this video and go, okay, got it, I'm good. No, these are your robots. You are building them, okay? You're not going to be able to send them to anyone to go, back to the factory to have them fixed, okay? You are the factory. You are the builder, okay? You are the expert. You have to become knowledgeable in these things. Understand how everything interacts and why things are the way they are. Um, and it will just save you a lot of heartache instead of just, blindly, you know, just, oh, nope, looks good to me. You guys are all smart, bright individuals. You would not be on the damn team if you weren't, okay? So, yeah. Um, avail yourself to the information that's provided, okay? Questions, ask me. For God's sake, ask. Comments, constructive criticism, fine. But I think we got a winner here. Is it perfect? Yeah. What is? Who knows? Will it work? Again, 99.9% sure. So there we go, guys. It's not as, any guy with a Chinese mill in his basement could make some of these parts. I realize that. But then I also realize that we're working on this is a very unique robot. And there's just some things that you're just going to have to outsource. You're going to have to send it off somewhere to somebody that can CNC, steel, things of that nature. And I would like to add that, again, these two pieces will have to be pretty precise. You're not going to be able to have a rough surface on one and the other. It's going to need to, and there's going to be grease in there. But the more precise you can get that to where there's, it slips in there nice and then just spins right around, the longer the system's going to last. If you have it machined and you have a bunch of chatter marks in there, if you haven't come up with some way of, honing that out or boring that out or putting like the eccentric lobe on a lathe and turning it to get a nice, and then, yeah, rough finishes are going to make for very rough operation and it's not going to last long. If it's done correctly, and this is one of those things where precision is gonna pretty much be the key to it. Yeah, you're gonna, yep, it's gonna slip right together, nice and yeah. It's got to be done right. If it isn't done right, will it work? Maybe. Will it last? No, probably not. Okay. So there you go, guys. There's a design. I'm going to get with Kyle. I have to create the G code to do the aluminum parts. I'm going to talk to John at NYCCNC. I'm also going to be sending this link out to him and Ed. Hi, guys. And see if they can't, you won't machine me a set of these parts in steel for the prototype because I simply can't machine steel. Could I make them out of aluminum and test them? Yeah, I probably could. The thing is it might end up just breaking because again, my main concern is this arm. I might not even be able to thoroughly test it before that thin 300 thousandths wall just snaps due to the forces. So that's about it, guys. Sorry for my rant. Dear God, 29 minutes, 33 seconds. Yeah, okay, we're keeping this under a half an hour. So that's about it, guys. Talk to you later. Bye for now. And the monkey pushes the button when he can find the button. Come on. Here we go. Ah.